Okay, today we are starting out our notes with a quick review on our angle-based theorem. This is something we've touched on briefly before. In our isosceles triangles, if I'm told that I have congruent segments, that means that my angles opposite those segments are congruent. Or if I'm just given that I have congruent base angles, that means that the sides opposite those angles are going to be congruent. So we're going to use that information in a new way today. Starting out with just a couple examples on solving for x. So in this first problem here, I'm going to color code which of my angles are congruent, because that's an important part of this, is identifying which angles are the opposite angles. So in my first triangle here, I've got the tick marks. So the 68-degree angle and the other base angle are the congruent angles. And in my second triangle with my tick marks, the angle that has x in it and this other base angle are my congruent angles. So we're going to kind of have to work our way around and stair-step our way over. So if this angle is 68, this angle is also 68. That interruption. So if both of these angles are 68, I can find that last angle by subtracting the sum of those two angles from 180, because my three angles have to add up to 180, and that gives me 44. So this third angle in that triangle is 44. Now, this tick mark here tells me that the two angles together form a right angle, meaning they add to 90 degrees. So to find that pink angle, I'm going to subtract 44 from 90, and that gives me 46. So this angle is 46, and because this angle is congruent, it's also going to be 46. So x is 46. On to example 2. I have my tick marks that tell me this 70-degree angle and the other base angle are congruent. So that means this angle is 70. If I know those two angles, I can find the third angle by subtracting their sum from 180. And that's going to leave me with 40. So this is a 40-degree angle. And I have vertical angles here. So this one's also going to be 40 degrees. So this is also 40 degrees. And looking at the tick marks on my bottom triangle, these pink angles are my congruent angles. So this other angle is also 40 degrees, which means x is 40. Number 3. With my tick marks on the triangle on the left, these are my congruent angles. So these angles are both 64, so I find that third angle by subtracting their sum from 180. And that leaves me with 52. And just like on number 1, these two angles form a right angle, so I find that other side by subtracting from 90, and that leaves us with 38. Then looking at our triangle on the right side, this angle 2 is congruent to that 38-degree angle according to my tick marks. So angle 2 is equal to x plus 44. And because it's congruent to that 38-degree angle, that means that 38 is equal to x plus 44. So to find x, I'm going to subtract 44 on both sides, and we get that x is equal to negative 6. Okay, one more. Here on number 4, I'm told that my base angles are congruent, which means the sides opposite those two angles are congruent. So 10 is equal to x plus 16. So to find x, we're going to subtract 6, and we get that x is negative 6. Okay. Now we are going to go on to the back side and work two quick proofs. This is our equidistance theorem, and it pertains to our perpendicular bisector. This was also on your notes, but again, we did not go super in-depth on it. So recall, a perpendicular bisector is a line that bisects, so splits it in half, and is perpendicular to a segment. Now, on your notes that you've seen previously, it did tell you that the perpendicular bisector is always equidistant from the endpoints of the segment that it bisects. So if we can prove that we have 2 points that are both equidistant from the endpoints of a segment, then the line connecting those 2 points determines the perpendicular bisector. And we're going to use that theorem for these two proofs. So starting on this first one, angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4, and our diagram is already marked that way. Now, we already know from our base angle theorem that if 1 and 2 are congruent angles, then the sides opposite them are congruent. So AB is going to be congruent to AD, and if 3 is congruent to 4, then with the same theorem, BC is going to be congruent to DC. So let's get that down in our proof. Angle 1 is congruent to angle 2, Angle 3 is congruent to angle 4. And we're given both of those. And from that information, we concluded that AB is congruent to AD and BC is congruent to DC. Now, I need an if-then statement to support that. And if you go to page 11 of your dominoes, the second and third theorems on that page are the base angle theorems. So, if the base angles of a triangle are congruent, then the sides opposite them are congruent. Okay, so let's talk about what we've just shown here. If AB is congruent to AD, that means that the distance of AB, the length of AB, or the distance is the same as the distance or the length of AD. So the distance between A and B and A and D is the same. So A is equidistant from the endpoints, okay? And if BC is congruent to DC, that means that C is the same distance away from B as it is from D. So C is also equidistant from the endpoints. So we have 2 points that are equidistant from the endpoints of the segment. So the line connecting those 2 points is our perpendicular bisector. So we've shown all that we need to show, and we can say that AE is the perpendicular bisector of BD, and our reason is going to be this first theorem. If 2 points are equal distance from the endpoints of a segment, then they determine the perpendicular bisector of the segment. Okay. We're going to practice this one more time on our next proof here. We're given that triangle ABC is isosceles with AB congruent to AC, and then E is the midpoint of BC. So what that tells us is E splits BC into 2 congruent segments. So BE is also going to be congruent to CE. So if we're wanting to show that AE is also perpendicular to BC, we already know it bisects it because it splits it in half. But if it were to be the perpendicular bisector, I need 2 points that are equidistant from the endpoints. So if AB is congruent to AC, like we already discussed, that means A is equidistant from the endpoints. And this one's a little bit different because E is the other point that's equidistant. With BE being congruent to CE, that means that B is the same distance away from E as C is. So E is our other equidistant point. With those points A and E being equidistant from the endpoints, we know that AE is also perpendicular. So let's get this all down on paper. We're starting with our givens. So our isosceles triangle and our midpoint. So that midpoint is what told us BE was congruent to EC, so we need to get that down. And this definition is on the front page of your dominoes. If a point is the midpoint, then it divides the segment into 2 congruent segments. So we were already given that AB is congruent to AC, so that takes care of A being equidistant. And here with BE being congruent to CE, that takes care of E being equidistant. So we have 2 points that are equidistant. So we can say that AE is perpendicular to BC because of our same reason from the first proof. If 2 points are equidistant from the endpoints of a segment, then they determine the perpendicular bisector. And that takes care of our equidistant proofs.